So today we're going to finish chapter 21, talking about acetals and related compounds. Then we'll go into chapter 22, carboxylic acid derivatives, starting off with our introductory material on structure and nomenclature. We have an important announcement. We will have a quiz on Tuesday. We're having a quiz on Tuesday because this is I'm sure you're all aware, Monday is a holiday. Hopefully you're all aware that this is the week where the university has decreed that Tuesday is a Monday. So we're getting a holiday from our Tuesday classes, no holiday from our Monday, Wednesday, Friday classes. So we have class Tuesday, Wednesday, and Friday next week. Okay, so please remember that. Okay. All right, so we talked about acetals at the end of class on Wednesday, about how we use this Dean Stark trap as a means of removing the water and driving the equilibrium to completion. And we rely on an azeotrope. The benzene and the water form a constant boiling mixture that causes that water to be removed. Cyclic acetals are a common form of acetal. If we use a diol, if we use one equivalent of a diol as opposed to two equivalents of a monoalcohol, then the product we obtain will have a ring, because both alcohols that are reacting are going to be from the same molecule, and they'll form a ring. So this is ethylene glycol, a very, very common diol. It's part of antifreeze. And it will react with aldehydes or ketones to make 5-membered cyclic acetals. Okay? And we'll talk about these in a moment. These are useful. They're actually useful as protecting groups. They're a bit more stable than the acyclic acetals because of the stable ring size that we're forming. So the mechanism for acetal formation has two parts to it. In the first part, we react one equivalent of our alcohol with catalytic acid and the aldehyde or ketone, and we generate a species called a hemiacetal. Hemi stands for half. This is half of an acetal because it just has one ether group on the oxygen and one OH group. Okay? And then in the second half of the mechanism, we eliminate out water, and we replace that with our second equivalent of an alcohol, generating the acetal. If we are making a cyclic acetal, this second step is going to be an intramolecular reaction, because the second OH group would be part of the R group of the hemiacetal. But if it's an acyclic acetal, we would have two different equivalents of our alcohols reacting to generate the acetal. This first equilibrium is usually quite unfavored. It's very, very similar to forming a hydrate from an aldehyde or a ketone. In fact, the mechanism is the same. And so this equilibrium is unfavorable. It doesn't, and in order to drive it to completion, we have to remove the water at the end. Okay, so we typically would have a very, very small amount of a hemiacetal present, but any hemiacetal that gets formed can be converted into the acetal essentially irreversibly if we are removing the water. So the mechanism, here's the mechanism of acetal formation with acid catalysis. It's the exact same mechanism we showed you for acid catalyzed hydrate formation. We're just using an alcohol as the nucleophile instead of water. If you replace this R with an H, you would get the same mechanism that we learned earlier. Okay, so protonate the carbonyl, generating a resonance stabilized cation. Attack that. We could draw it with either of the contributors. They chose the minor. I usually like to choose the major. But either way, you get to this intermediate, which has to be deprotonated to generate the hemiacetal intermediate. Any questions? Okay, so let's draw the second part of the mechanism. And it's different from the first, but it's going to be very similar to the mechanisms that we showed you for making imines and making enamines. We're going to have the same sort of steps that we had in imine and enamine formation. Okay, so we start off with our hemiacetal. In the first step, we're going to protonate the alcohol. Here's our toluene sulfonic acid. Okay, so we've generated tosylate, our conjugate base. We've protonated our OH, generating this oxonium ion. Okay, so you might ask, why are we protonating the alcohol and not protonating the ether? Well, we can protonate either one. We do protonate either one. If we protonate the ether, we just go back to this intermediate shown here on the screen. Okay, remember this is an equilibrium, and so both are happening. But if we're removing water later on, we're going to be able to drive it to the right. Okay, so when we're drawing the mechanism, we're drawing it in the forward direction with our equilibrium arrows, recognizing that it can go either way. Okay, we protonate that oxygen. That sets us up to eliminate water. We've seen that before. When we formed imines and enamines, we had a step where a nitrogen would assist in the elimination of water. Here we have an oxygen assisting in the elimination of water. Okay. And at this step, if we have our Dean Stark trap set up, we're removing the water by the azeotrope. So that's how we can drive the reaction towards the right. And then we'll get this cationic intermediate. It's resonance stabilized. I've drawn the major contributor for you. The minor contributor would have a positive charge on the carbon. Okay. And now at this point, we would use our second equivalent of alcohol. Or if this was an intramolecular, if it was a diol, we would have another OH group as part of R, and that would be attacking the carbon. But the way I'm drawing it here, it's the intermolecular version, where our alcohol attacks. Okay, and that gives us this cationic intermediate, which needs to be deprotonated. And so here we're going to use our toluene sulfonic acid, conjugate base. Let's draw that a little closer. Deprotonating that oxygen, generating our acetal product, and reforming our toluene sulfonic acid. The reaction is catalytic in toluene sulfonic acid. Okay? So this is how we convert a hemiacetal into an acetal using steps that we've seen previously. Proton transfer steps, elimination of water. We've seen elimination of water when we were forming imines and enamines. And then nucleophilic attack, followed by deprotonation. Okay. Any questions about making acetals? Yes. Could you use two different alcohols? Probably not, because if you added them to the reaction mixture together, then you'd get mixtures of products where you would have both alcohols on one compound, mixture of alcohols on other compounds. So you'd get mixtures of products. If you tried to add one alcohol second, that would be a problem, because I mentioned you can't stop at the acetal, because unless you're removing water, you're hardly going to have any of the acetal, right? So you have to remove water which converts that hemiacetal into the acetal. So it's not a situation where you could add one equivalent, stop at the acetal, then add another equivalent to get the acetal. So I've never seen mixed acetals before. We're either going to have two of the same alcohol or we're going to have a diol of this type. Okay, other questions? So because this is an equilibrium, we can reverse the process, meaning we can take an acetal, we can treat it with an alcohol in the presence of a strong acid, or not an alcohol, water. We can treat it with water in the presence of a strong acid, and we can hydrolyze the acetal and generate an aldehyde or a ketone. This sample problem asks you to draw a mechanism for that, and we should be able to draw the mechanism. Last semester, we learned something called the principle of microscopic reversibility. We learned that in an equilibrium process, the same intermediates and transition states are encountered in either direction. Okay, so all the intermediates that are shown here are the same intermediates that you would have in forming an acetal. You just encounter them in the opposite direction. Okay. Notice that if you're forming to drive the equilibrium towards the ketone or the aldehyde, you want to use excess water, and therefore we want to use an acid that is soluble in water. So when we are forming acetals, we use benzene, we use toluene sulfonic acid, which is soluble in organic solvents. When we are hydrolyzing acetals or converting them to aldehydes or ketones, we're going to use sulfuric acid because sulfuric acid is water soluble. Okay? But other than the nature of the acid, the mechanism is the same, just in the opposite direction as we go through. Part one, we're converting acetal to hemiacetal. Part two, we're converting hemiacetal to the aldehyde or ketone. One thing I'll mention about this mechanism is that all of the intermediates are either positively charged or neutral. And that's a sign that you've drawn a correct mechanism. If you are using acid as one of your reagents, it's going to be very, very rare to have a negatively charged intermediate, except for the conjugate base of that acid, right? That's the only negatively charged species you would have. So if we look at the intermediates we're getting here, other than that conjugate base, positively charged, positively charged, positively charged, right? Neutral, positively charged, neutral. So we're just, they're always going to be either positively charged or neutral. So if you're drawing a mechanism and you're using acid and you end up with a negatively charged species, unless it's the conjugate base, then you've probably done something wrong. Okay, so that's a good way to check your work. And the corollary is true. If you were using base, you would expect all the intermediates to be neutral or negatively charged. Okay, any questions? So the utility of our acetals is primarily as protecting groups for aldehydes or ketones. So let's say we have a molecule that has an ester and a ketone in it. Let's say we want to reduce the ester, but not the ketone. Do we have any reagents that will reduce esters, but not ketones? The answer is no, we don't. Any reagent that's going to reduce a ketone is also, or going to reduce an ester, is also going to reduce a ketone. So we cannot reduce the ester without reducing the ketone. So what would we do? We would protect the ketone, then reduce the ester, and then deprotect. Okay? So if we react this molecule with ethylene glycol, toluene sulfonic acid, benzene, we heat it up to be able to remove the water as it's formed. We're going to form a cyclic acetal. Okay. Now the key here is that we don't form an acetal from the ester carbonyl. This is important. We learned in chapter 20 that aldehydes and ketones are more reactive than esters. And so we're only making acetals from aldehydes and ketones. We're not making them from esters. Okay? So only the ketone carbonyl reacts to make our cyclic acetal. The ester carbonyl does not. Okay? All right, now we're to this point. What reagent do we use to reduce esters to primary alcohols? Our strongest reducing agent. What is it? We have a test on Friday, so if you don't know it now, you have a limited amount of time to learn it. Lithium aluminum hydride. Okay, if we use lithium aluminum hydride, followed by the addition of water, we're going to reduce that ester to the primary alcohol. Okay. And so now that we've accomplished our reduction, we need to do our deprotection. As you see on the screen, we just add sulfuric acid and water, and that's going to remove the acetal, giving us our desired product. Okay, so we couldn't go from the starting material to the product in one step, but using a protecting group, we're able to accomplish this transformation. Any questions? All right, so in these protecting groups, these cyclic acetals are stable to a variety of reagents. They're stable to base. They're stable to reducing agents, as you've seen here. They're stable to oxidizing agents, but they are reactive in the presence of acid and water. So they're good protecting groups as long as you're not using acid or water in your reaction. So in response to the earlier question, I told you that hemiacetals can't be isolated because the equilibrium is unfavorable and you have to convert them to the acetal and remove water for them to be stable. But there is one exception. There is one type of hemiacetal that is stable, that forms spontaneously and can be isolated. And that is a cyclic hemiacetal that is forming either a 5-membered ring or a 6-membered ring. So if we have an alcohol, 1, 2, 3, 4, 5, and an aldehyde in the same molecule, then that alcohol, in the presence of acid, trace amounts of acid or base, can attack the carbonyl carbon. And in this case, we would generate a 6-membered cyclic hemiacetal. Because 6-membered rings are stable, they're strain-free, this type of acetal is favored. At equilibrium, you would have a 94:6 ratio of these two compounds. Okay. One other thing to notice is that our 6-membered cyclic acetal has a new stereocenter, so this compound would be formed as a racemic mixture. Okay. And we can do that with a 5-membered ring as well. So 5 and 6-membered cyclic acetals are going to be thermodynamically stable. Here the ratio is not quite as favorable because I'll put that over here. The 5-membered ring has a tiny amount of ring strain that's not present in the 6-membered ring. Okay. So the mechanism for formation of a cyclic cyclic hemiacetal is the same as the acyclic one. It's just that your nucleophilic attack is an intramolecular process forming a ring. So first we protonate the carbonyl, then our nucleophile attacks, and then our conjugate base deprotonates, giving us that product. And if you dissolve these molecules in water, there's usually enough trace acid in the water to promote this reaction. Okay? So you can isolate cyclic hemiacetals. If you want to, you can also convert cyclic hemiacetals into acetals. So if we were to take this cyclic acetal, if we were to react it with methanol and some kind of acid, we would be able to convert that cyclic hemiacetal into a cyclic acetal. And of course, it would be a racemic mixture because this would be a stereocenter. Okay? So, and we could draw a mechanism for this. It would be the same as the mechanism up here. Protonate the oxygen, lose water, have the methanol attack, and then deprotonate. So why are cyclic hemiacetals and acetals important? They are the components of carbohydrates, which are the most abundant biomolecules in the world. So when we talk about biomass, which is the mass of all of the molecules in nature, carbohydrates make up the largest component of that biomass. And carbohydrates exist as cyclic hemiacetals and cyclic acetals. Here we have glucose, our most common carbohydrate, and you see that it has this cyclic hemiacetal. Notice that carbohydrates have many more OH groups than the simple cyclic hemiacetals we drew on the board. And then we can link carbohydrates together. We can link sugars together to make polysaccharides. This is a disaccharide with two rings linked together. And whenever you have disaccharides or polysaccharides, you have cyclic acetals as well as the cyclic hemiacetals. Okay? So we have a chapter on carbohydrates later on. It's either 26 or 27. So before too long, we're going to be learning a lot about carbohydrates. Now, we just need to know that they are cyclic hemiacetals and cyclic acetals, and that their formation is thermodynamically favorable, unlike acyclic hemiacetals. And this slide shows that for us. If you add up these percentages, you get 100. And so that tells you that the amount of A present is going to be really, really small, right? So at equilibrium, you have less than 1% of the acyclic form of glucose. This is the acyclic form of glucose. And most of glucose is in the cyclic form. Because glucose has several other stereocenters, then when we cyclize and we form a new stereocenter, the products are diastereomers of each other as opposed to enantiomers. And so we do not get a one-to-one mixture because in this case, the diastereomer with the equatorial OH group is more stable than the diastereomer with the axial OH group. And so we get about a 2-to-1 mixture of those two isomers at equilibrium and less than 1% of the acyclic aldehyde at equilibrium. Okay? Any questions about cyclic hemiacetals or carbohydrates? Okay, then we will move on to chapter 22. So in chapter 22, we're going to be focusing on carboxylic acids and their derivatives and the characteristic reaction of carboxylic acid derivatives, which is nucleophilic acyl substitution. We've already learned about nucleophilic acyl substitution. We learned about it in chapter 20, and we used organometallic reagents as nucleophiles or metal hydride reagents as nucleophiles. In this chapter, we're going to be using heteroatom nucleophiles in our nucleophilic acyl substitutions. Okay? So on the screen here, we have, this is an acyl group. We know what acyl groups look like. We've seen them before. Here's our carboxylic acid. It's up at the top of the slide because it's the parent compound from which all these derivatives are derived. And then the derivatives themselves are listed in order of descending reactivity or increasing stability. So the acid chloride is going to be the most reactive and the least stable of these compounds. The amide is going to be the most stable and the least reactive. And we're going to explain why in a few minutes. There's one exception to that. For some strange reason, the book has put esters and thioesters out of order in this particular figure. Okay, so a thioester is going to be less stable and more reactive than an ester. And we'll explain why in a moment. Okay, so let's talk about some vocabulary first that is important for understanding our carboxylic acid derivatives. So if we look at the anhydride, the term anhydride means without water. Something that's anhydrous doesn't have water in it. If you look at an anhydride, it looks like we've glued two carboxylic acid molecules together and removed water in the process. And so that's where the anhydride name comes from. It comes from it being two carboxylic acids minus water. Okay? So we can have a couple different types of anhydrides. We can have symmetrical anhydrides. These would be derived from two equivalents of the same carboxylic acid. Okay, so we would call this a symmetrical anhydride. And then if we have two different groups, if it's derived from two different acids, we would call that a mixed anhydride. And then we can also have the anhydride in a ring. And we would refer to that as a cyclic anhydride. Okay. So just a little bit of vocabulary associated with anhydrides. Amides have some vocabulary, and it's vocabulary we've used before, and it's describing the number of carbon-nitrogen bonds we have in our amides. So when we have an NH2 attached to our carbonyl carbon, we refer to that as a primary amide because we have one carbon-nitrogen bond. If we attach an R group to that nitrogen, now we have a secondary amide. If we attach another R group, it can be the same or different. I've drawn it different, but it doesn't really matter. That is going to be a tertiary amide. Okay, any questions? Cyclic esters and amides have their own special terms. A cyclic ester is known as a lactone, and a cyclic amide is known as a lactam. And we use Greek letters to indicate the size of the ring, and I'll show you how this works. So this molecule is a cyclic ester, so we would refer to it as a lactone. And then we count the carbons moving away from the carbonyl. This is our alpha carbon, beta carbon, gamma carbon, delta carbon. The delta carbon is bonded to the oxygen, so this molecule is a delta lactone. So a delta lactone would be a six-membered cyclic ester. Okay? The same terminology applies to cyclic amides. So this is a lactam. Four-membered ring, so alpha beta. This is a beta lactam. You may have heard the term beta lactam before. Penicillin is the most famous, most prominent member of a class of compounds known as the beta lactam antibiotics. So there's a class of antibiotics that contain this four-membered cyclic amide, and that four-membered cyclic amide is critical to its mode of action. We'll talk about that later on, about how that four-membered ring allows penicillin and other antibiotics to kill bacteria. Okay? So a little bit of vocabulary describing the compounds in this chapter. There's one type of compound in this chapter that does not have a carbonyl group, and that is the nitrile. So nitriles have cyano groups. Right? This is a nitrile. So why are nitriles in this chapter? Well, a nitrile has 3 bonds between carbon and nitrogen. Okay? All of our carboxylic acid derivatives have 3 bonds between the carbonyl carbon and heteroatoms. Okay? 2 of those bonds are to the carbonyl oxygen, and then 1 is to another atom that's either an oxygen, a nitrogen, a sulfur, a chlorine, what have you. So because we have 3 of these carbon heteroatom bonds to the same carbon, then a nitrile is going to actually undergo similar types of reactions as carboxylic acid derivatives. Right? We're going to have a partial positive charge on this carbon due to the polarization of that triple bond, similar to the partial positive charge we have on the carbonyl carbon of our carboxylic acid derivatives. Okay, so nitriles fit in this chapter even though they do not have a carbonyl carbon. Okay, so let's talk now about the stability, the relative stabilities of the compounds in this chapter. Okay, so our carboxylic acid derivatives have this generic structure. We use Z as an abbreviation for the heteroatoms that are bonded to the carbonyl carbon. And we have minor contributors. Anytime we have a carbonyl compound, we know we have a minor contributor we can draw with a negative charge on the oxygen and a positive charge on the carbon. When we have a carboxylic acid or its derivatives, we have a second minor contributor we can draw because we have 1 or more lone pairs on Z that can be donated. Allowing us to draw a resonance structure looking like this. Okay? And the more basic Z is, the more able it is to donate that lone pair. And so the more prominent this minor contributor becomes. Right? So the more basic Z is, the more prominent that minor contributor becomes. We can see the impact of that when we draw the hybrid structure. So here's the hybrid structure. We're going to have a partial negative charge on the oxygen and partial positive charges on the carbon and on Z. The more prominent this minor contributor is, the larger the partial positive charge on Z is, and the smaller the partial positive charge on carbon is. Okay? So as we increase the basicity of Z, we're increasing this partial positive charge and decreasing that partial positive charge. If we're decreasing the partial positive charge on the carbon, then we're making the molecule less electrophilic at the carbonyl carbon and therefore less reactive. We're making it more stable by resonance because we're increasing the delocalization of charge onto that Z, but that increase in stability is correlated with a decrease in reactivity because we're shrinking the partial positive charge on the carbon. Any questions about that? So that allows us to draw a hierarchy in terms of reactivity. Well, we'll do it in terms of stability. Okay, this is going to be relative stability, starting from our least stable carboxylic acid derivative and going to the most stable. Okay? So our acid chloride is going to be the least stable because chloride is the least basic of all of the groups attached to the carbonyl carbon. That chlorine is highly electronegative, holding on to its electrons tightly. Plus, it is a third row element, so the bond is longer. That also leads to less efficient donation. Okay, so acid chloride is going to be our most reactive, least stable carboxylic acid derivative, followed by the anhydride. Okay, we're going to skip thioesters and phosphates right now. We're going to come back to them in a minute because we typically encounter the acyl phosphates and the thioesters in biochemistry rather than in reactions in a lab in a flask. Okay, so we're going to discuss them separately. So skipping them, then the next one is going to be the ester, which is going to be roughly equivalent to the carboxylic acid. Both of these compounds have oxygens donating to the carbonyl carbon. And then our most stable, least reactive derivative is going to be the amide, because that nitrogen is the most basic of our Z groups attached to a carbonyl carbon. So if you're looking here in the middle, you see we've said that the anhydride, which has an oxygen attached to the carbonyl carbon, is going to be less stable or more reactive than the ester or the carboxylic acid, both of which also have oxygens attached to the carbonyl carbon. Why? Why is this oxygen-containing molecule less stable and more reactive than these? It has to do with the ability of that oxygen to donate to the carbonyl carbon. Right? It has to do with the prominence or lack thereof of this resonance structure. Any ideas? Okay, Brady? Okay, very good. So we have two carbonyl groups attached to that oxygen as opposed to one over here. And your oxygen is only going to donate to one of them. You're not going to have a +2 charge, as you noted, on that oxygen. And so the electron density of this oxygen is split between two carbonyls. So each one gets half the electron density as you would get over here. And so that makes the anhydride less stable and more reactive than the ester or the carboxylic acid. Question? You can tune the reactivity of anhydrides by putting electron withdrawing groups to make it more reactive, or donating groups to make it less reactive. You can do that. That's not something we're going to get into in this class. We're just going to kind of lump them all together. But yes, in the real world, there are some anhydrides that are more reactive than others based on the type of R group that you have. So there's a table here in the book that's relating pKa values of the conjugate acids of our Z groups to the relative stability or the relative reactivity of our carboxylic acid derivatives. Okay, so least basic at the top, most basic at the bottom. And we see that based on the pKa's of the conjugate acid. Our least basic Z group has the most acidic conjugate acid. Our most basic Z group has the least acidic conjugate acid. So from this, we can see where the acyl phosphates and the thioesters fit in. We see the pKa's of their conjugate acids. And so we can see that they're going to fall in between the anhydrides and the esters in terms of their relative reactivity. Okay? Which is good because we don't want acid chlorides or anhydrides floating through our veins. Those are going to be too reactive in biochemical reactions. Conversely, esters are going to be too stable for nucleophilic acyl substitution in the body. But the thioesters and the acyl phosphates have the right balance between stability and reactivity to be useful in nucleophilic acyl substitution in nature. Okay? Any questions about this hierarchy of reactivity and stability? So you shouldn't have to memorize this table. You should be able to understand, based on the principles we learned in Chapter 2 of predicting relative acidity, you should understand the ordering of the pKa's of these compounds. And therefore, you should understand why acid chlorides are the most reactive of our carboxylic acid derivatives, and the amides are the least reactive. Okay. All right. Let's talk about our favorite subject of nomenclature. Now, the good news, well, the bad news is we have a whole bunch of types of compounds to learn how to name in this chapter. But the good news is that their names are derived from carboxylic acids. Okay, so we don't have to learn much more because we've already learned nomenclature for carboxylic acids. Okay, so we're going to start with acid chlorides. And acid chlorides, they're going to be named the same way as the parent acid, but we're going to drop the ic acid, or we're going to drop the carboxylic acid part, and we're going to put ill chloride on the end. Okay? Now, it's easier to just look at examples than it is to write out rules for this. Okay, so we'll just go through an example, a couple examples. What's the parent carboxylic acid of this acid chloride? Okay, it's not a trick question. One of our most common carboxylic acids. What do we call it? Acetic acid. Okay, so acetic acid, we're going to drop the ic acid. So this is what we're left with when we drop the ic acid. And then we put ill chloride on the end. Okay, so this is acetyl chloride. Okay. With cyclic acid chlorides, it's a little bit different. Okay. What would this be called if it were a carboxylic acid? I'll give you the first part. It would be cyclohexane. And then what would come next? Carboxylic acid. Okay. Okay, in the case of a cyclic acid chloride, we drop our ic acid, but then for some reason, we have to change the X to an N, and we call it a carbonyl chloride instead of a carboxyl chloride. Okay, so this would be cyclohexane carbonyl chloride. All right, so you make that X to N switch. That's the one quirky thing of our acid chloride nomenclature when it's a cyclic acid chloride with that group coming off of the ring. Okay, any questions? All right, now the good news about naming acyl phosphates is it's exactly the same as naming acid chlorides. You just have the word phosphate instead of chloride. Okay, so phosphate instead of chloride, and now you can name any acyl phosphate. Okay, so that's really, really easy. Anhydrides, we just replace the word acid with anhydride. Okay, so that's pretty straightforward. Okay, so if it is a symmetrical anhydride, then it's really easy. So this is a symmetrical anhydride derived from acetic acid. So we just write acetic, and we replace the acid with anhydride. Okay. If it is a mixed anhydride, then we have to name both of the groups. Okay. So what would this be if it were a carboxylic acid? This part of the molecule, what would we call that carboxylic acid? Benzoic. Okay. So that would be benzoic acid. What would we call this part? A 3-carbon carboxylic acid? It has a common name, but for this one, the IUPAC is easier to use. So the IUPAC name for 3-carbon carboxylic acid would be what? Propanoic, okay? So we've got benzoic acid and propanoic acid. As you might imagine, we order those in alphabetical order. So this molecule would be called benzoic propanoic anhydride. Okay. Any questions on naming anhydrides? Okay, let's look at esters now. And esters have 2 components to them. They have an alkyl group. This is the alkyl group. And they have an acyl group. Okay? So we have to name each component of the ester. We have to name the alkyl group, and we have to name the acyl group. Okay? So the order in which we do that is we name the alkyl group first. And then we name the acyl group. And that acyl group is going to end in either 8 or O8. Okay? So we'll show you what we mean by that. And that's going to be based on whether the acid's name would end in ic acid or oic acid. If the acid that acyl group is derived from ends in ic acid, then you just have 8. If it ended in oic acid, then you would have O8. Okay? All right, this is one of our simplest esters. It's used in the lab all the time. It's a component of many fingernail polish removers. What is our alkyl group? 2-carbon alkyl group. That's ethyl. Okay. What is our acyl group? What carboxylic acid is that acyl group derived from? Okay, that's acetic acid. So the acetic acid, we drop the ic acid, and we add 8. So this molecule is called ethyl acetate. Any questions? Let's do a cyclic one. Okay. What's our alkyl group? Okay, this is a tert-butyl group. This 4 carbons here. So tert-butyl. What's the carboxylic acid? It would be benzoic if this were an aromatic ring. Cyclohexane carboxylic acid. Okay. So we call that tert-butyl cyclohexane carboxylate. Okay. So we drop the ic acid and put 8. We don't change the X to an N the way that we do with acid chlorides. Okay. Why we do it here and not here, don't know. But somebody decided that that's how we're going to do it. Okay. Any questions about naming esters? Okay, thioesters are very similar. We're not going to get into it. You just put an S in front of the alkyl group, and then you stick thio in the name in front of the 8. Last one we'll do are amides. And amides, remember we have primary, secondary, and tertiary amides. So the naming is going to be a little bit different in each case. The primary amide is going to be the easiest. We're just going to drop the ic acid and add amide. Okay, so sticking with our simple example, acetic acid, we drop the ic acid and we add amide. Okay, so that's just called acetamide. Now, if we have a secondary amide, we now have an alkyl group attached to our nitrogen. And we have to name that alkyl group, just like we did with esters. We have to name that alkyl group. But when that alkyl group is on a nitrogen, when it's on any atom other than an oxygen, we have to use a letter associated with that. So we have to put an N in the front of the name to indicate that the alkyl group is attached to a nitrogen. Then we name our alkyl group. Right? So this molecule is called N-ethyl. And then what carboxylic acid is it derived from? Benzoic. So this is N-ethyl benzamide. All right. When we have a tertiary amide, we have two alkyl groups on the nitrogen. And IUPAC has decided we need two N's to indicate that. If it's the same alkyl group, we would use di. If they were different alkyl groups, we would just split them up, right? You'd say N-ethyl, N-methyl. But if it's the same, we use di. And so in this case, it's going to be NN-dimethyl. What's our one carbon carboxylic acid called? Formic acid, okay? So this would be formamide. NN-dimethyl formamide, also abbreviated as DMF. Does anyone remember what we used DMF for last semester? It was one of our polar aprotic solvents, okay? This is a polar solvent. It is aprotic. It has no OHs, no NHs, and so the DMF abbreviation is derived from this IUPAC name. Any questions about naming amides? Yes? Yes. If it's two different groups, you would split the ends up. So yeah, it's kind of quirky, but I don't make the rules. I just enforce them. So, all right. Have a good 3-day weekend. Please come to class on Tuesday prepared for our quiz.